Okay, line symmetry, the first one is what you've known as symmetry, like since elementary school. It's like where you draw a line through a shape and then it's like a mirror image on both sides. So for this first section, it says state whether the shape appears to have line symmetry. Say yes or no. If so, draw all the lines of symmetry and state like how many there are. So for number one, for this regular triangle, you draw a line of symmetry right here. So yes, it does have line symmetry. And then it asks how many lines of symmetry it has. Now we're going to draw them in a second. But anytime you have a regular shape with all the sides that are congruent, you can just count the number of sides or count the corners, and that's how many lines of symmetry you're going to have. So this triangle is going to have 3. It has one right here. It's a mirror image on both sides. And then it also has one right here. So it has 3 lines of symmetry. Okay, the next one, I'm going to try to draw lines of symmetry, of course. So I draw a line maybe here, and then you'll realize that it doesn't reflect the same on both sides. Like this should have a point to it, and it doesn't. So it doesn't have a line of symmetry that way, maybe this way. But again, this pointy part doesn't reflect over on this side like it's supposed to. So therefore, this is no line symmetry. And then number 3, looking for a line of symmetry, obviously not here. Maybe here, but if you look at it closely, this is like a 90-degree angle, and then this is not. So therefore, no line symmetry. And then number 4 right here, this one does have line symmetry. We could draw a line right here. So yes, line symmetry. And then you could also draw a line right here, and it would reflect the same on both sides. So it has 2 lines of symmetry. Someone also asked today about like a diagonal. No, like this would have to be here, and it's not. The one where a diagonal does work would be a square. Like with a square, you can draw a diagonal and it does reflect the same on both sides. Okay. What do you mean? Wait, what did you say? Okay. Okay, then from here, I'm going to have you guys try it right here. So I want you to go through and say whether it has line symmetry or not, like yes or no, and then put how many lines of symmetry it has. So try it yourself. I'm going to freeze. I'm going to answer it too, and then we'll compare answers. Okay, so here's what I got. Compare your answers, make sure you got it right, and we'll move on to the next thing. Okay, next is something you probably haven't seen before called rotational symmetry. What rotational symmetry is can you rotate the shape from like a center, and can you rotate it onto itself without rotating it 360 degrees? So this shape, we could rotate it just like one turn here and it would land on itself. So this would be yes to rotational symmetry. And then for each one, we're going to write the order and also the magnitude. Magnitude. And so order refers to how many times it would land on itself in a 360-degree turn. So it's like how many spikes there are. 1, 2, 3 in this case. And then to find the magnitude, that's how many degrees you would turn it to turn onto itself. So 360 degrees divided by 3 gives you 120 degrees. So every 120 degrees it lands in that same location or orientation. So the next one, we have to identify the center right here that is rotating around. And then we're determining whether it has rotational symmetry. It looks like if you turned it just a little bit, it would land on itself for each of these spikes. So yes to rotational symmetry. And then we need to identify the order and the magnitude. So order is how many spikes it has or where it lands on itself. So 1, 2, 3, 4, 5, 6, 7, 8. And then to find the degree, it would need to rotate to land on itself. We just take 360 degrees divided by 8, and it comes out to 45 degrees. So every 45 degrees, it lands on itself. And number 7, I would put the center right here. Can it land on itself without having to go all the way around? Yes, it looks like if you spun it 180 degrees, it would land on itself. So yes to rotational symmetry, order, and magnitude. So for order, be like right here and here, so 2. And then magnitude would be 360 degrees divided by 2, and it comes out to 180 degrees. So every 180 degrees, it lands on itself, which is what we said in the beginning anyway. And then for 8, where to put the center, maybe like right here. You notice that in order to rotate this onto itself, you'd have to rotate it a full 360 degrees. So therefore, it has no rotational symmetry. Okay, so then we're going to try it over here. There's a few examples, so I want you to try it. So you're going to put yes or no to whether it has rotational symmetry, and then put the order and magnitude, order and magnitude, order and magnitude for each. If you don't have a calculator on you, just write the operation that you're going to do, and then I'll tell you the exact number when we go over it. Freezing this. Okay, so here's what I got. 360 divided by 5 is 72 degrees. So like every 72 degrees, it would land on itself. And then 360 divided by 16 little spikes here is 22.5. Number 4 kind of caught people off guard. So I would put like the 2 right here, and then it would have to spin 180 degrees to land on itself. You could, yeah, it'd be 2. It would either be here and here, or the top and bottom. I guess it doesn't matter. It would just take 180 degrees to turn on top of itself. Okay. Last part. State whether the figure has plane symmetry, axis symmetry, both or neither. So write down plane symmetry and axis symmetry, and I'll explain what it is in a second. You might be able to predict, I don't know, axis symmetry. So what plane symmetry is can you slice it with a plane and it's the same on both sides? So just slice it with a plane, and is it the same on both sides? And then axis symmetry is when you spin around a central axis. I'm going to try to show these on this picture as best I can. So like slicing this with a plane, like right in the middle, would you get the same thing on both sides? And that would be a yes. So it has plane symmetry. And then axis symmetry is like if there was a central axis, like a pole in the middle of the shape, could you spin this around the pole and get it to land on itself before you spin it 360 degrees? So that would be a yes. In this case, you could spin it like 90 degrees and it would land on itself. Okay, so let's try this with cone. Does it have plane symmetry? Can you slice it and like have the same thing on both sides of that slice? Yes. And for axis symmetry, can you spin it around a pole like this And will it land on itself before it goes all the way around? Yes, it would land on itself the whole time. Okay, and then on the other side, we're going to try it. Got it all down. Okay, then over here is where you're going to try it. So does it have plane symmetry? And does it have axis symmetry? Plane symmetry. And does it have axis symmetry? Okay, here's the answers and I'll show you why. So plane symmetry and axis symmetry, yes to both for this. And then this one has plane symmetry, but not axis symmetry. So plane symmetry for this, you could slice it this way and it would be the same on both sides. You could also slice it like down the center too with a plane and it would be the same on both sides. And then for axis symmetry, if there was like a pole down the center like this, you could rotate it 180 degrees and it would land on itself. So that has both. Then over here, the plane symmetry caught me off guard at first because I was trying to slice it like this, and it doesn't have plane symmetry that way because this would be like a 90-degree angle and this is not. But at some point, a student pointed out that you could slice it like down this way, and then you could have half and half that way to show it the best. But yes, so it has plane symmetry because you could slice it there. And then axis symmetry, you could try, but it's not going to work. You'd have to flip it all the way around 360 degrees for it to land on itself, so no to axis symmetry. And then number 9, a word problem. A paddle wheel on a steamboat is driven by a steam engine that rotates paddles attached to a wheel propeller. So like paddles, cool. If a paddle wheel contains 8, whoa, sorry, my bad. I don't know if that's better, but okay. 18 evenly spaced paddles. 18 of these. And then we're asked for the order and magnitude. So the order would be 18, and then 360 divided by 18 would be 20 degrees. And that's as well. Okay, so now you have the rest of the class. Get your homework done. And Alex, if you need to get it done, ready, set, go. Okay.